Now, the curve with equation 2 log of 8 minus x, now that's that curve there, notice.
Yeah.
It's labelled there.
Yep.
Meets this line y equals x, which of course has a gradient of what?
Y equals x. No, 1, sorry.
1, and therefore is at an angle of?
45 degrees.
Yes, good.
I hadn't thought about that before, but logic would say that 90 divided by 2 is 45. So
it's useful and important to, because of course that's why reverse tan of 1 is?
Reverse tan of 1 is, reverse tan of 1 is.
In other words, what angle has a tan value of 1? Well, SOHCAHTOA tells us that tan means what?
Tan means opposite over adjacent.
So notice that that really is the rise over the run, isn't it? Opposite over adjacent.
Oh right, yeah.
So tan really is like
tan 45 equals 1 then.
Yes, quite.
Yeah. Okay.
Anyway,
yeah.
back to this.
Why not on
so here's. Yep. Sorry.
Oh, it's an iteration question. Okay, I was just reading the question.
Sure.
Well, I haven't done iteration since GCSE. Does it change?
I don't think this isn't much worse than a GCSE question on iteration.
Is it just the fact that it has a login?
Yeah, really, I think.
But ultimately, you're just putting it into a calculator, aren't you? That's how. I mean, in an exam, that's how I would do an iteration. I would do the sort of.
Yeah, but they also in part A, what they're making you do here is making sure you understand what's going on.
3 over A over 4.
Yes, how would you show that alpha, the perfect solution to x, is, even though we won't find the perfect solution?
Oh, so the x value of the point that they cross is between 3 and 4. Is that basically what they're asking?
Between x values of 3 and 4, that's right. So here's an x value of 4, 3's about there, and the perfect x value, the solution to where these meet, would be somewhere between 3 and 4, yeah?
Right. Yeah. So the way of doing that. Well, first, wouldn't it be, would you not put 4 in as the x value?
Yes.
On each?
You could.
And make
them
equal each other.
Yep. Sorry?
Oh, yeah, no, I think I know how to do this. Is it something about the sign flipping?
Well, yeah.
Well, actually, no, one being greater than the other on one side of the point, and then on the other side.
And that's the other way of looking at it. The sign flipping is preferable, really, generally speaking. What was it? It was basically like that, wasn't it? And to show that it's somewhere between 3 and 4, you could show that when you put 3 into both of the two functions, when you put 3 into the x value here and the x value here, because this was y equals x, wasn't it? And this was y equals 2 log of 8 minus x, I think. When you put 3, when you put 3 into both of these, you could show, which I think you did express in words perfectly well, that one of them was above the other. And then when you put 4 in, you could show that that had flipped and it was the other way round.
Yeah.
So you show that this function is above the other function at 3, whereas this function is above the other function at 4.
Yeah, I think the thing that I was saying about the sign flipping is that basically when the point is on the x-axis.
Yes, but it's better to turn this really into that. It's clearer, really, even though you don't know what this combination is going to turn out like. So how do we combine these to look at it in this other way?
How do you combine those to look at it?
Well, if we're saying that one thing is equal to another, that also means that the one thing minus the other
is 0.
is 0, yes. Which might seem
Oh,
complicate
and then
matters. Yeah?
no, I understand.
It
Yeah, I
complicates
think I
matters
understand what
because
you're
we
saying.
don't really know what this function is going to look like, but let's not care. Let's say somehow or other when you subtract that from that, you get this weird function. But it does turn into what I think you were referring to as a sign flipping.
Yes.
Instead of having to compare two things at 3 and two things at 4, you just say you get a value at 3 and a value at 4, and notice what?
That as you change the x, yeah, the sign of the
whole thing, the difference.
The whole thing, yeah, the difference is negative. Is that? Well, it depends which way around you do it, I guess. But
yes, the sign flips from whatever it was for one of them to whatever it is at the other one.
Yeah.
I mean, I don't know if I've drawn this the right way round, have I? Would it be?
You may have.
It would be positive at 3 because that one minus that one would be positive.
Yes.
Whereas that one minus that one would be negative. So it would kind of look like this, whatever the shape of the curve is, you know, which is very
who knows, because it's kind of weird, but yeah.
Yeah.
Right. So the subtraction. So for the subtraction, you would just put in 2 log 8 minus 3.
Yeah. So that one
minus 3 equals
exactly. That would
0.
be 2 log 5 minus 3, whatever that is. Have you got a calculator there? I've left mine downstairs.
Why 5 minus 3? Yeah, I do have a calculator, but why 5 minus 3? I thought it was 8.
8 minus x, though, and x is 3.
Oh, yeah, that's fair enough. Yeah.
Oh, yeah, because I wasn't putting brackets there. I wasn't being clear, though, that my brackets were there.
Oh, no, okay, yeah. Right, so 2 log 5 minus 3 equals 0.219 to 3 significant figures. I don't want to write it all down.
And anyway, it's positive. And then the other one?
And then the other one would be, is that for value 8 minus 4, so 4 minus 4.
Yeah, 2 log.
Minus 1.23.
Which is less than 0. So point made, as long as you either draw a graph or just say, look, I understand what's happened somehow or other.
Yeah.
However you want to. Just make it short and make sure you get those 2 points. I'm sure you will if you, but you know, if you put those 2 values clearly into those. I suppose you ought to reference somehow the change of the switch of some sort. Right. And now they're saying, okay, here's the graph in a bit more detail, and the student uses this original version, which is to say 2 log of 8 minus x equals x, because that's this way of showing it, isn't it, where the 2 graphs are crossing. I mean, identifying that point there is like putting this equal to that.
Yes.
And that does turn into a useful iteration formula.
Does it?
Yes. Sometimes this happens. If you failed to make x the subject, because you've still got an x over here, you might have a perfectly good iteration formula for getting progressively closer to your solution. Nonetheless, that's what these that's how these iteration formulae work when they do work.
Okay.
So each next improved value of x is 2 times the natural log of 8 minus the previous approximation.
Okay.
So all you have to do is what you did in GCSE, put 4 and then press equals.
4 equals, then yeah.
And then say 2 log of 8 minus answer.
2 log of 8 minus answer, is that it? Yeah.
And then just display for them, look, if that's x1 equals 4, then my calculator is telling me x2 equals, and when you press equals now,
2.77 around.
Yeah, x3 equals?
x3 equals 3.31.
x4?
x4 is 3.09.
Now, I don't know what hints it gives as to determine whether or not it can be used to find an approximation, justifying your answer. You just want to indicate that you're convinced that these values are converging towards a value of some sort.
I think they are actually, because the next one is 3.18.
I mean, you might even.
Oh yeah, no. I mean, I don't. I wouldn't know how to write that, but I think it looks fairly.
Well, like this, and it might be worth continuing until you can say, look, I've noticed that it's stabilizing to X number of decimal places.
Yes. Yeah. It's stabilizing to 2 decimal places, I think.
By when? What were your X? Or have you lost count? Possibly.
Oh no. Oh, sorry, no. If you mean when it's always actually wait, 3.
I mean, if you keep pressing equals, it'll stabilize to as many decimal places as you like. You see.
Yeah. 3.16, which was x7. By x to the 9, it's stable. There's been 2 x 3.15.
Yeah, great.
So,
yeah.
Yeah. Okay. I would write that better in an exam, but
yeah, they've left it open. You know, as long as you investigate and report.
Yeah, report the right findings.
Yes, quite. Okay. That's all they wanted there, really. What they haven't asked for is the cobweb diagram.
The cobweb. What's the cobweb diagram?
Which is okay. So starting at 4. Well, from this one, we got a y value of 3.77, didn't we?
Yes. Actually, wait, no. For which?
And then we put that new value into the same one.
Oh, yes.
So we went from an x value of 4, and then we put this y value of 3.77 as our next x value.
Yeah.
So we went up to the curve again and found our new y value. And then we used the y equals x again to turn our new y value into an x value. And then hopefully, damn, in this drawing it didn't work. I must have drawn, it's going further and further away. The opposite ought to happen.
Okay. The opposite ought to happen. Yeah. Okay. I see the concept, but yeah, I'm.
Yeah.
Yeah.
Unless I did it all exactly backwards, did I? First x value is 4. That ought to, supposing I'd started a bit clearer there and gone to there, to there, to there. No, it must be that I need, if I use theirs.
It will work with theirs, won't it? Because, or will it? Sometimes it wouldn't, because they don't have to draw it accurate.
But it has. We've shown that it ought to work. We've shown that it does work. So we ought to be able to draw the diagram called a cobweb diagram, just to make it sound even more scary than it needs to. Now then, so if we go to 4, so our first x value of 4 goes to a y value of
something 3.77.
3.77. Ah, but then perhaps they've drawn it wrong so that we wouldn't do it this way. And then we get the next value. Oh, but look, it is working.
Oh, it is working, and it gets really small, but
yeah.
Oh, that actually makes a lot of sense.
Yes.
I'd never seen an iteration thing drawn like that before.
Well, I think that sometimes I think it's actually in the GCSE syllabus. But it's a scary topic to learn or teach.
I mean, I know iteration was, but I had never seen a question like that, and I think I would have seen one that required me to.
In the A-level syllabus, anyway, you need to be aware that there is a thing called a cobweb diagram, which, if the iteration formula works, it should operate like that just did. But my previous attempt didn't. Yeah, and then sometime. By the way, you know, it's interesting to see the reasons why it doesn't work. But I'm not sure if I can generalize offhand about why that is. But there's a related topic where you can. Have you heard of the Newton-Raphson formula?
I know the name, but I have no idea what it means because I've only ever seen it in a
Well, that's another method for approximating a solution where it's not available precisely. And this is a case in point. You won't solve 2 log of 8 minus x equals x algebraically. It'll just be unworkable, I think. So the best you can do, I mean, I'm not sure, but I don't think you could solve it, and you would make do with an approximation of this sort. And another method for approximating things you can't solve precisely is called the Newton-Raphson formula, where you take your initial approximation x1, let's call it xn. So whatever approximation you've got, xn, you subtract the function, and this is assuming that your function is crossing, you're trying to find where something crosses the x-axis.
Yeah.
So you've got it in this formulation. Then the Newton-Raphson equation says, okay, for each iteration, subtract your function of that divided by the derivative at that point, and you will improve it repeatedly. But then where it doesn't work is if this denominator is too small, everything goes haywire.
Is it Newton as in Isaac Newton? Is
that yes. I don't know the historical context, but I presume it's Newton, as a lot of calculus is Newton, because
is calculus just what is calculus? Is it integration and differentiation? Or is it...
Yes. I mean, and of course, it's short for the infinitesimal calculus. So calculus is just an old word for calculating. So the word itself doesn't refer to what it really is. It's just short for infinitesimal calculus, which does refer to the fact that you are, you remember how you find the derivative from first principles? Have we done that? Where we say, let's find the derivative of an approximation to a tangent.
Oh yes, and then you keep making the distance smaller.
Yeah, and you get smaller and smaller, so you're looking at infinitesimal.
That tends to 0 and all that. So yeah, okay.
So Newton did, for the purposes of mechanics and forces and stuff, he did invent the infinitesimal calculus, along with, but there was the big controversy between him and Leibniz. Leibniz invented the dy dx notation.
Oh, okay.
Whereas Newton would have written x with a dot over it to mean dx with respect to time t. And then the second derivative would be x double dot. And then Lagrange, I think, is this. So you've got three alternatives here, haven't you? You've got f dashed.
The only one I'm not sure that I've seen is the x with the dot over it. But
yes, that's only in physics.
That's only in physics.
Sorry?
That's only in physics. Oh, no, that's fine.
Yeah. So you will be expected to recognize that, and
I do. Yeah, well, that's not a problem. Yeah.
Between f dashed and dy dx, basically. So yeah, Newton-Raphson. I've no idea who Raphson is, but anyway, that's the Newton-Raphson iteration formula.
Yeah. Okay.
I think no, it's not in the booklet. I do. Yes, it is. Yes, I think it's in the booklet.
Well, it's not impossible to remember, really.
No, quite. It's not. It's not impossible to understand either. It's quite nice. Let's say here's your formula.
Yeah.
Try again. Let's say here's your f formula. Try again. That's better. Let's say that's your formula f. And let's say this is your xn. Then this is your f of, this is what the function you get, the value you get resulting from doing the function arithmetic to that input of xn, isn't it? Up here.
Yeah.
So that's this height here, isn't it? Now you want to get closer to here, don't you?
Yes.
This is the point you look at. This is the x value you really want, and this is where you are.
Yeah.
And all you're going to do then is draw a straight line path. If you come down this, if you slide down this tangent line, then you will have improved matters, won't you?
Oh, and that's a differentiated version because that's the gradient at that point. Yeah, okay, that makes sense.
Yeah. You want to subtract that fraction that you are able to subtract. That fraction there that you are subtracting from your current best estimate is going to give you exactly this amount here to subtract. And you can even see why that is, because what you're doing is you're dividing by the gradient here. You're dividing this length by the gradient, which is going to find you this there.
Yeah. Yeah, okay.
So that amount there, that thing there is exactly f over f dashed.
Yeah.
Because that much is f. And then you divide by that gradient. You have to think about the geometry a bit. But that's Newton-Raphson. But it doesn't work if the denominator is too small. Right.
Okay. Yeah, because if the denominator is too small, then it means that. Yeah.
Well, of course, sometimes. I mean, the other day we were doing one, and the answer, they said, "Why can't you use Newton-Raphson here?" And the answer was that the denominator was not only small but 0.
And you can't divide by 0.
Yes. So
because because if the denominator is too small, because you're dividing, you're going to get such a high number that.
Exactly. Yes. Yeah. Quite. And presumably it's for related reasons that a very small denominator would also make it explode unacceptably or be unreliable in some way. I'm not sure. I haven't really thought about that too deeply. But that's roughly the principle. Okay, and that's that one.